Hello, thanks for the invitation to talk. I'm going to tell you about some of the work we've been doing recently on Memristor crossbar-based multi-core processing systems, essentially what we can do with Memristor crossbar-based systems. So what we first started doing in this area was looking at device models. So we came up with some device models, and this model is fairly flexible. It can model devices from several different sources. And we're using this device model in SPICE for almost all of the results I'll be showing you later in this talk. We're updating the device now to include impact of noise, and most of the circuit simulations I showed you actually do incorporate the noise factor or stochasticity within the device behavior. And recently this model that we had was incorporated into XYCE, a parallel SPICE simulator from Sandia. This is an email I got on January 20th saying that they incorporate our device. All right, so with Memristor, what we want to do with Memristors is essentially have analog processing of neurons. So the way this works is you have your inputs come in on this way. On this side, these circles represent the memristors. So I have a voltage coming in. That voltage multiplied by the conductance of this memristor gives me a current. So I've got multiplication taking place here. So that's Ohm's law. And all these currents sum up over here. That's Kirchhoff's law. And so I'm getting a multiply-add done using this circuit. So this circuit here is representing a single neuron. And a pair of memristors are used to represent a weight. So depending on the conductance between the two memristors, you have either positive weight or negative weight. And then I can take a collection of these neurons together and represent a layer of neurons. So here I have 7 neurons in the first layer. That's represented by these 7 comparators in this Memristor crossbar. The outputs of these comparators are going into the second layer, Memristor crossbar representing the second layer of neurons. And so I have another output here. So now I have a 2-layer Memristor two-layer neural network represented using Memristor circuits. So we then said, okay, let's take this system and see what we can get in terms of overall system performance. So to look at system performance, what we wanted to do was have a system like this where we had a tiled array of neural cores and the cores connected using routing networks. And to make sure we got everything right, we actually implemented this in digital form on an FPGA. In the digital form, we have the router. We actually have a memory array, multipliers and adders and accumulators. So all of this is done. And then in the Memristor system, what we're going to do is just replace this memory array and these multiplier adders and accumulators with a Memristor crossbar. Everything else is going to stay the same. So this is a mixed signal. This is, in the Memristor system, this will be a mixed signal design where we have data processed in analog form over here, but transferred between the cores in digital form. And here's the output that these are the actual inputs and outputs from our FPGA implementing an edge detection algorithm written in neural form. So we looked at this. As I said, we evaluated every single component of this system, including static power loss, the time for routing, so we actually simulated the Memristor crossbar also in SPICE to look at the timing and power consumption. And these are the results we got. So we looked at several applications, deep networks, edge detection, motion estimation, optical characterization, with the inputs coming in at approximately 30 frames per second. And we said, okay, if we wanted to do this, we have 3 options. One is a multi-core RISC processing system. One is a digital design based on this FPGA-based approach, but converted into an ASIC form. And the third is that, again, that multi-core system, but using memristors. And what you see is we get significant efficiencies using the Memristor system over, say, a RISC processor or a digital design. Now, what's interesting is, in this design, we had image inputs coming in at 30 frames per second. And during the gap between inputs coming in, there's a huge amount of delay. And that is burning a huge amount of static power. So if you take that static power out, assume that the inputs come in one after another without that 30 frames per second constraint, what you see is that the energy efficiencies become a lot higher for the Memristor system. So instead of being, say, 34,000 times, it's now about 1 million times more efficient. Then we started saying, okay, let's now try to do some online learning. So this design that I'm talking about over here does not have any online learning. So to do online learning, what we first did was we tried to implement backpropagation. And one of the key challenges with our circuit is that we have 2 memristors per synapse, and that makes backpropagation not easy to do. So what we had to do was use 2 different kinds of neuron circuits. We used one circuit for the forward pass and a different kind of circuit for the backward pass, and this approach allowed us to use the same crossbar in both the forward and backward passes, so that if we don't ever have to copy memristor weights around, and we can still use the full range of 2 memristors to get greater sort of weights represented. So we took this design and we implemented an autoencoder with this. So we have 2 layers of this neural structure over here. And we simulated that in SPICed, and you can see these results over here. So we have 3 application sets, and this is what we had before training. This is what we get after training. So this is unsupervised training using memristor crossbar-based circuits. And you can see we get fairly good separation after training compared to before training. Here's another implementation, another use of that kind of a circuit for anomaly detection using the KDD dataset for network traffic. And what you see over here, these are considered normal packets, and these are considered anomalous packets. And you see a fairly decent separation. Depending on where you put your separation line, we get about 96.6% anomaly packet detection with about 4% false positive rate. Okay, so then we took this design and we said, okay, let's try to do a deep learning system where we actually do the entire deep learning framework using memristor crossbar-based processing systems. So we designed a multi-core system. So you have each of these circles over here represents a neural core, and then you have the connecting router. And this design has that backpropagation type of circuit I showed you earlier. And we looked at several different applications. So you can see the efficiency of the recognition accuracy of this system compared to a software system. So the blue bars here represent our Memristor system, and the yellow bars represent floating point implementation of the same training and testing data set done in MATLAB. And there is some loss in accuracy, but it's not that significant. What's interesting is the performance over, say, a Tesla K20. And you see significant savings in energy over the Tesla for training, and even more for recognition. Now, the reason that the training energy efficiency is less is that there is some serial weight update going on in the training side, whereas in the recognition side, everything is being done in parallel. So you get more parallel, faster runtimes, and thus lower energy consumption using the Memristor system. And so these are things we are trying to work and fix. Now, this comparison is not fair. The reason it's not fair is because the GPU is doing floating point operations, number one. Number two, we're using the whole power of the GPU card here, so we don't, that includes the fan and everything else on the system. But we try to make it as efficient, as fair as possible. We transferred all the data to the GPU, ran the system 1,000 times, and did the timing collection only while we were doing the actual application. So I want to talk about a few more applications we did. We looked at implementing convolution neural networks on the GPUs, on the Memristor crossbar systems. This is just recognition. We haven't done the training part of it yet. We've also done some cybersecurity applications. We implemented signature-based snort detection by actually implementing all of the state machines that you see in your snort rules implemented using Memristor crossbar systems. So for instance, here's a regular expression. We converted that into state machines, and then we can implement that state machine in using a set of Memristor crossbar approaches. So we get fairly low energy consumption, about 2.2 nanowatts per rule, and decent throughput. And we also have, as I showed you earlier, anomaly detection. So just a few more slides. One of the things we're looking at, why is it not moving? So one of the things we're looking at now is device fabrication. One thing we noticed while doing our SPICE simulations is that we really need devices that are that are slow or more highly tunable. So to go from the complete off state to the complete on state, or switch the resistance range fully, we need to have a device that takes a long pulsing time. So we started looking at some devices, and these are some recent results that we have. And finally, we started looking also at implementing some applications on the IBM TrueNorth system, which we're hoping to eventually get onto the Memristor system. And the application is an autonomous agent that's being designed at the Air Force Research Lab. So we're working on implementing that actually right now. And finally, these are my collaborators and sponsors. Thank you.
Thank you. So let me ask a question. I mean, Memristors have a lot of variability, which you didn't take into account for your performance numbers.
Yes.
So what would you expect? How would it affect your results?
So Memristors have a lot of variability in them. We did take that into consideration. One of the things we are actively working on right now is updating our Memristor model to make it more accurate. And we're waiting on data from our collaborators, Sandia, for instance, to give us some more information about how the Memristors behave so we can update our model.